Okay, so we're looking at improper integral practice, and there are two basic types of improper integrals here. So the first type is when you're integrating from a constant to infinity, or negative infinity to a constant, or negative infinity to infinity. These types of improper integrals are said to be improper integrals on infinite intervals. So this is where your interval is infinite, because it either goes from a to infinity, or negative infinity to a, or the entire real number line. So that's type 1. Type 2 is where we have a situation where, for example, we take the integral from negative 4 to 4 of 1 over x dx. Note that on the interval from negative 4 to 4, our function is unbounded at 0. Not that it's just undefined at 0, but it's unbounded, which means that the limit as x approaches 0, let's say from the right, that's going to go to infinity. So those are our two types. So the first type is on an infinite interval, and the second type is where we have an unbounded function. So it's almost like type 1, you have a function that kind of just goes on forever this way, or forever that way, or both. And then type 2, you have a function that shoots up or shoots down at some value in its interval where it's being integrated over. So we're going to do a bunch of examples from the handout improper integral practice. Problem number 1 is not an improper integral. I put it there just so that you could see that it's not an example of an improper integral. This is on the interval from 0 to 2. And if you remember what this function looks like, this is the greatest integer function, which goes like this. And we're going from 0 to 2. So we only care about the area bounded by the curve from 0 to 2. So notice that even though it doesn't have continuity on this interval, it's still integrable, and it's not unbounded. This function from 0 to 2 is not unbounded. 2 is the maximum, and, 1 is the maximum, although technically 2 is, I guess, and 0 is the minimum. And the idea here is to find the area. And if you use the geometric argument, we get that the area is 1. But we also know that this function is piecewise from last year. This equals 0 when x is between 0 and 1, 1 when x is between 1 and 2, and 2 when x is between 2 and 3. So what we can do is when we take this integral, we can break it up piecewise from 0 to 1 of 0, and then from 1 to 2 of 1. And you're going to say, well, what about the very end point over here? Because there it jumps up. Well, that area underneath that 1 point is 0, because it has no width. There's no rectangle there. So when you integrate, the integral of 0 is, well, 0 from 0 to 1. And the integral of 1 is 1 from 1 to 2. So this becomes 0 minus 0 plus 2 minus 1 is 1, which is the same area that we found here. So the answer to number 1 is 1. Now, that's not an example of an improper integral. So what is? Well, problem number 2 is. Problem number 2 is integrating a function on the interval where the function is unbounded. And so we have f of x equals 1 over x from 0 to 1, not including 0. So since we're not including 0, we could integrate from 0 to 1, but this is going to wind up with a problem. Before, when we integrated the greatest integer function, we went from 1 to 2, and 2 wasn't a problem because the function is bounded at 2. There it is. It's defined and it's bounded. But here, our function is not defined and it's not bounded at 0. If we graph this guy at 0, this thing shoots up. So in order to handle this, we need to use limits. So you pick your favorite letter. In this case, I'll choose A. And we let A approach 0 from the right. Now, why the right? Well, if I'm on the interval from 0 to 1, and I'm on this interval, if I move to the right, I'm going to approach 1. If I move to the left, I'm going to approach 0. Notice that as I move to the left, I'm approaching 0 from the right. I'm not coming from the left of 0. I'm coming from the right of 0, which is why we approach from the right. And now we do what we would do with any other problem. We bring the limit with us, and we take the antiderivative. And the antiderivative of 1 over x is ln absolute x, from a to 1. And now we just plug in, and we get ln of 1 minus ln of a. ln of 1 is 0, but as 0 approaches, as a approaches 0 from the right, this approaches negative infinity. So really, if these were numbers, we would say this approaches infinity. This means that this improper integral is unbounded and it diverges, meaning that the area is larger than any number we can name. No matter what number you come up with, the area will still be larger. So for problem 2, the area is no nice number. It's not bounded, so it diverges. Problem 3 is similar. Problem 3, we have 1 over rad 2 minus x as x goes from 1 to 2. And note again that this function is defined everywhere in this open interval, or this closed, mixed closed open interval, except at 2. 2 is not in the interval, but the function is not bounded at 2. So once again, when we do this, take the limit. We'll take n for Noel. As n approaches 2 from the left, because this time I'm coming at 2 from the left in my interval. Here's 1, and then here's 2, and if I'm approaching 2 from 1, I'm moving right, but I'm approaching 2 from the left of the integral from 1 to n of our function with respect to x. And here we're going to need to do a u substitution. U is 2 minus x. Du is minus dx. So negative du is dx. So now we take the limit as n approaches 2 from the left of. So this becomes minus du from here. The u becomes 2 minus x, so this is square root of u. And now we need our limits of integration. When x is 1, plug in 1, and we get that u is 1, because 2 minus, in this case, 1 is 1. And then on the top, we would have 2 minus n. Okay? And now this is the limit as n approaches 2 from the left of the integral from 1 to 2 minus n negative. This is just u to the negative 1/2 du. And it doesn't seem to be writing that. There it is. Okay. And now when we integrate, we get that this is u to the 1/2 divided by 1/2, which is the same thing as 2. And then we bring this minus sign with us from 1 to 2 minus n. And so that's equal to the limit as n approaches 2 from the left of negative 2 times 2 minus n to the 1/2 minus 1 to the 1/2. Okay. And so this is the limit. Actually, I could probably evaluate the limit right now. So let's see, this is negative 2 times. As n approaches 2 from the left, n approaches 2 from the left, 2 minus n would approach 2 minus 2, which is 0. And when we take things to the 1/2, that's just square rooting them. So this winds up being negative 2 times negative 1, which is 2. So as opposed to the previous problem, here our area is bounded. If we graph this, it would look like the area goes on forever, and the region is actually unbounded going up, but the actual area is a nice number. It's 2. So that's one type of improper integral. The other type of improper integral is like the one in problem 4. Here, we're not on an unbounded interval, rather, we're not on an interval where our function is unbounded. Here, we're on an interval where the interval itself is unbounded. Note that I can go as far to the right as I want. So here, if we're going to integrate, we integrate from 1 to infinity of 1 over x cubed dx. But this doesn't make mathematical sense. These limits of integration are supposed to be numerical. So instead of putting an infinity there, because later on we wouldn't be able to plug infinity in, we pick our favorite letter, C for Chester, and we'll let C go to infinity. So this way, instead of going to infinity there, we wind up going to C, or C for Cetron. And now, we can anti-differentiate this. Remember that this is the same thing, and I'll do this step, as x to the negative 3. So now we have the limit as c approaches infinity of. So we add 1 to the exponent, and then divide by that new exponent. And this goes from 1 to c dx. So this is the limit as c approaches infinity of. And I will simplify this into negative 1 over 2x squared from 1 to c. That's just algebra because x to the negative 2 is 1 over. Okay. And now this is the limit as c approaches infinity of negative 1 over 2c squared minus negative 1 over 2 times 1. Now as c goes to infinity, c squared would go to infinity, 2 times c squared would go to infinity, and 1 over that would go to 0. So this is 0 plus a half, so this is a half. So interestingly here, we have an unbounded interval, and we're going from 1 to infinity of 1 over x cubed. 1 over x cubed looks kind of like this, and if I go from 1 all the way out, this region has an area of exactly 1/2. And the rest of the problems are very similar. Yeah, there are a few catches in here. Problem 5 is similar to problem 4. Problem 6, nobody seems to like the absolute value, so we'll do that one. This is 1 over rad absolute x, from negative 1 to 1. And notice without the absolute value, I wouldn't be able to have negatives, because I can't take the square root of a negative number. But here, the only problem now is 0, because when x approaches 0, this thing winds up shooting up, like that. So once again, what we have to do is we have to take the integral from negative 1 to 1 of 1 over rad absolute x dx. Now, the problem is at 0. So what we're going to do is we're going to break up this integral into 2 other integrals about 0. Because the problem is at 0, we need to address that problem directly. We can't just glaze over it. I'll show you how to not do this problem in a second. But this is the correct way. And now, from negative 1 to 0, I never actually get to 0 because the function there is unbounded. So we're going to have to take some limits here. So we'll take the limit as, I don't know, b approaches 0 from the left, because when we go from negative 1 to 0, negative 1 to 0, we're approaching 0 from the left of, so let's see, negative 1 to b of this, plus, and now we need another limit, so we'll take c, and here we approach 0 from the right, because if I'm on the interval from 0 to 1, then the only numbers I have in that interval are numbers to the right of 0. So this would be c to 1. Now the next step would be to deal with the absolute value. If you recall, just a little side note, this is the absolute value function. And notice the very first integral we're taking goes from negative 1 to something really close to 0. So we're always going to be less than 0 there. So our absolute value of x is going to be negative x there. So this is going to be the limit as b approaches 0 from the left of, and this is going to look a little weird, but that's okay, negative 1 to b, of 1 over the square root of negative x. And before you say, wait a minute, you can't take the square root of a negative number, remember, x itself is negative. So this is a negative of a negative number, so it will be positive. And then similarly, in this second integral, we're between 0 and 1, so the absolute value is always going to be positive. So there we have that. Now, I can rewrite these to help out a little bit. This is from negative 1 to b of negative x to the negative 1/2 plus limit as c approaches 0 from the right of integral c to 1 of x to the negative 1/2 dx. Oops, don't forget the dx's. Now, the integral on the right is a straight power rule. So this is the limit as c approaches 0 from the right of, this would be x to the 1/2 divided by 1/2, or x to the 1/2 times 2. On the left here, we could do a u substitution. If you can see it, you don't have to, but I'm still going to do it because it's not always that easy to see. So here we'll let u equal negative x, du equals negative dx, which means negative du is dx. And so now this integral on the left becomes the limit as b approaches 0 from the left of, well, the dx is now negative du. The u is negative 1/2 x. And now let's see. When x is negative 1, u is 1. And when x is b, u is negative b. U is. And we'll just copy this guy down here. So now I'm going to do the integration on the left. And again, if you don't need to use the u, you don't have to, if you recognize what this is going to become. Some people don't need it. But otherwise, it can't hurt to do it anyway. So let's see. This is the same antiderivative we had before. Oops. See that? Almost messed that up. That should be to the negative 1/2. Whoops. Sorry about that. So this is now 2u to the 1/2, but there's a minus in front, from 1 to negative b, plus the limit as c goes from 0, c approaches 0, of 2x to the 1/2 from c to 1. Okay. So now we can use the first part of the fundamental theorem to plug in. So this is negative 2 square root of u from 1 to b. So that means I have to plug in, well, you know what? I'm going to do this first, just to make this even easier to see. Again, you don't have to show all of these steps, but I'm doing it just so I don't make a mistake. So then we have the limit as b approaches 0 from the left of negative 2 rad negative b minus negative 2 rad 1, and then plus the limit as c approaches 0 from the right of 2 rad 1 minus 2 rad c. And you'll notice that this negative b here is important because b is approaching 0 from the left, meaning all of the values of b are going to be negative. So when I plug in a value for b, I get negative, and negative negative is positive, which means the square root of a positive number, and that exists, which is good. So as b approaches 0, this square root becomes negative 2 rad 0 plus 2 rad 1, and this becomes plus 2 rad 1 minus 2 rad 0. So this is 0 plus 2 plus 2 minus 0, or 4. So that was a little involved, but the answer turns out to be 4. There are others that involve u substitutions, such as 9 or 10. 8 is an interesting problem. 8 is going to wind up diverging. In fact, if you do problems 7 and 8, you're going to wind up with either an infinity or a negative infinity as your answer, and those diverge. 5, you'll wind up with a number, 9 and 10, I'm not 100% sure, but you've got to do a U substitution with those. And then there's just more practice after that. Various other problems. Let's see. 11, you have to let some variable approach 0 from the right. In fact, 11 is almost identical to 6. This part of 6. So problem 11 is literally just that part of 6. Problem 12 is very similar, except you're dealing with 1 over x squared. Problem 13 is going to wind up converging. Problem 14 should also converge. You should be using a U substitution. If there are any others of these that you want me to go over in particular, we'll do 17 just because it's a little different and it involves trig. Let's see, 17, integral from negative infinity to infinity of dx over x squared plus 9. So you should recognize at this point that if we try and do a U substitution, we fail. And we fail because our dx is here, but we don't have an x to go with it. There's no x there. So I can't use a U substitution. So instead, you have to recognize that this is one of those inverse trig guys. So for starters, in order to get this in that form, we're going to have to pull out a 9 from the denominator. So I'll factor out a 9 from the denominator, and then that becomes x squared over 9 plus 1. Or, if you will, 1/9 integral from negative infinity to infinity of dx over 1 plus x over 3 squared. And this is inverse tan. This is one of those that we recognize. So now we can do a quick U substitution. U equals x over 3. Du is going to be 1/3 dx. So 3 du is dx. And now notice here I didn't start writing my limits yet. We can also do a U substitution with the infinities, but we have to be careful, and I'll show you what I mean. So the 1/9 comes out, and let's see. dx is 3 du, and then the u is x over 3, so we get that. Now, as x goes to negative infinity, u also goes to negative infinity. And as x goes to positive infinity, u also goes to positive infinity. It doesn't always work that way. For example, if that were my u substitution, then this negative infinity would cause u to go to positive infinity. But that's not our equation, that's not our problem, at least not now. So at this point we have to use our limits, and we need 2 of them. So I'll multiply the outside here, and now we need the limit as b approaches negative infinity of the integral from b to, and it's just convention that if you're going from negative infinity to infinity, you go from your variable to 0. It doesn't have to be 0. It could be anything. It could be 1, it could be 5, it could be 20, but it's just convention to go to 0. But you'll see in a minute if that, in fact, I'll do this again so that you can see that it really doesn't matter. And then c goes to positive infinity of this 0 has to be the same as that 0. There was a theorem there that we could break up integrals. If you're going from a to b, you can go from a to some number and then some number to b. So this goes to c of this. Okay. So now, this is 3/9. This winds up being the limit as b approaches negative infinity of arctan of u. And so there. Plus the limit as c goes to positive infinity of arctan of u. And this goes from b to 0, and this goes from, I don't need that, 0 to c. And now it's a matter of plugging in and knowing our limits. Knowing our limits. 3/9 is 1/3, so this would be the limit as b approaches negative infinity of arctan of 0 minus arctan of b plus the limit as c goes to infinity of arctan of c minus arctan of 0 So this is 1/3. Now, as b goes to negative infinity, arctan goes to negative pi over 2. So this is arctan of 0 plus pi over 2, because this is minus a negative pi over 2, plus, as c goes to infinity, tangent goes to pi over, arctan goes to pi over 2 as well, and then this would be minus arctan of 0. And like I said before, where it doesn't matter what number we pick, it's because tan of 0 minus tan of 0 is 0. Those will always wind up canceling out. So we wind up with pi, and then times the 1/3 is pi over 3. There was one thing that I wanted to mention before that I completely forgot to, and it was in this problem, but you know what, I'll do a similar one. So it's important that you recognize when a function is unbounded. So just as an example, let's say that I wanted to do the integral from -1 to 1 of 1 over x squared dx. And I go, oh, okay, so then that means this is x to the -2 dx. So this is negative x to the -1 as we go from -1 to 1, because I anti-differentiated. And then let's see, that's negative 1 to the -1 minus negative 1 to the -1. So this becomes minus 1. This is minus 1, and we get -2. If you look at this region, though, notice that all of this region is above the x-axis. So this can't happen. And this is why we have improper integrals. The problem here is that this function that we're integrating is unbounded as x approaches 0. So in order to do this problem correctly, the integral from 1 to 1 of 1 over x squared dx, we would have to limit as b approaches 0 from the left, integral -1 to b 1 over x squared dx, plus limit as c approaches 0 from the right of c to 1 over x squared dx. Again, this isn't on the page, but I'm just trying to show you why we need these improper integrals. So this is negative x to the -1 from -1 to b as b goes to 0 from the left. And this is also negative x to the -1, this time as c goes to 0 from the right. And it might help to write this out a little bit here. So this is the limit as b approaches 0 from the left. X to the -1 is 1 over x. So we get negative 1 over b minus negative 1 over -1. Here we get plus, then we get negative 1 over 1 minus negative 1 over c as c goes to 0 from the right. And here's the problem. If we take these limits as z approaches 0 from the left, this winds up not existing, this limit. I mean, here, that you can add. That's your -2. But the problem is this, as we approach 0 from the left, winds up being negative infinity. This, as we approach 0 from the right, winds up being infinity. This integral diverges. It doesn't have an area. And the reason you got -2 before is because if you don't account for the 0 in between, it's almost like you're going negative infinity plus infinity is 0. And unfortunately, it's not. So the answer to this is that it diverges. You have to do it this way. This other way that I did it, this is incorrect. You cannot. If a function is unbounded on an interval, you need to take that into consideration. So I know this was long. It was about half an hour, but I did a bunch of problems. If you have any questions on any in particular, you can let me know. Just looking at this sheet, problem 15, you'll do a u substitution for -5x. Problem 16, you'll have to factor out the one. We did that one. Let's see. Problem 14, you do a u substitution, u equals 3 plus x. problem 17 is like problem 16. Oh, we did 17. 16 is like problem 17, except you're only starting at 3. 18, you do a u substitution for x squared plus 5. 19, you do a u substitution for the entire denominator, u equals 9 plus e to the negative 3x. 20 is some kind of inverse trig that I'm not really seeing right now, but we can get back to that. 21, the integral will diverge. 22, 23, and 24 all involve the inverse tan. You should know that the limit as x approaches infinity of arctan is pi over 2, and as x approaches infinity, negative infinity of arctan is negative pi over 2. 25, you would do a u substitution for x squared plus 5. And 26, you have no idea how to do. That's something that you should just look up. You might have gone over it in stats, but it is very interesting and is very important, but we have no way of actually computing that other than by looking it up. So that's it. I hope this video helps. And again, email me with any particular questions, and that's it. All right, have a good rest of the break. Bye-bye.